Assalamu alaikum students. This is your chemistry class. Here is your teacher Saima Ashraf and I am going to teach you the chapter 8, that is chemical reactivity. In this part of the chapter you are going to learn the term chemical reactivity, physical and chemical properties of metals. You are also going to learn about the electropositive character and its trends along periodic table. I will also tell you the position and electronic configuration of alkali and alkaline earth metals and also the differences in the ionization energies of alkali and alkaline earth metals. Introduction. First, I will explain you the term chemical reactivity. It is the tendency of a substance to undergo a chemical reaction. Chemical reaction is a chemical change, like rusting of iron. So basically the chemical reactivity is the ability or capacity of a substance to undergo a chemical change. There are many substances who have more capacity to undergo a chemical change. Those substances are called reactive, like iron rust when placed in the moist air, but gold or platinum do not rust in the moist air. So here the iron is the reactive substance while gold or platinum are not reactive. There are also many substances who are more reactive than others, means they have more capacity to undergo a chemical change. For example, chlorine. Chlorine is more reactive than iodine because it can displace iodine from its salt like potassium iodide. Here you can see in the equation that chlorine has displaced the iodine from potassium iodide and made another salt, potassium chloride. Similarly, iron is more reactive than copper, means it has more tendency to undergo a chemical change than copper. So it can displace the copper from copper sulfate. Like you can see in the equation that iron has displaced the copper from copper sulfate and made another compound, iron sulfate and copper metal. Metals. First, I will give you some examples of commonly used metals like aluminum, iron, copper, gold, silver. Aluminum is commonly used in the cooking utensils, like they are used in our kitchens. Iron is used in many things like gates, windows, doors, etc. Copper is used in electrical wires. Gold and silver are commonly used to make the jewelry. Now you are going to learn the properties of metals, physical properties as well as the chemical properties. Physical properties of metals means how the metals look physically or apparently. Metals are solids except mercury. Mercury is the only metal on the earth which is a liquid. They show metallic luster. Luster means shine, means they are shiny. They have moderate to high melting points. Moderate means not very high, not very low. Means they don't have the low melting points, whether they have moderate melting points or they have high melting points. They are good conductors of heat and electricity. Means heat and electricity can easily pass through them because they have the free electrons. They are malleable and ductile. Malleable means they can be transformed or changed into the sheaths, and ductile means they can be transformed or changed into the wires. So because of these properties, they can be transformed into different shapes by the processes like melting, molding, casting, hammering, and rolling. Melting is the change of the solid state into the liquid state. We can melt the metals and change them into different shapes by heating them. Casting and molding. During this process, we put the molten metal into the molds and we can give the shape to the metal. Hammering. We can hammer the metal and can change into the different shapes. We can roll them between the rollers and also give the different shapes to the metals by this process as well. Metals occupy the left side as well as the lower side of the periodic table. Most of the periodic table is covered by the metals. You can see all the elements in the blue boxes are metals. Means metals occupy the more part of the periodic table. They occupy the 3/4 of the periodic table. If you divide the Periodic table into four parts. Three parts are the metals. On the right side, you can see the elements in the yellow boxes are non-metals. You can see one non-metal on the left side, that is hydrogen, while all the elements on the right side in the green boxes are metalloids. Chemical properties of metals means how the metals undergo the chemical change or chemical reactions. Metals undergo the chemical reactions by losing the electrons. When the metals lose the electron, they form the ions with the positive charge, which are called cations. That's why metals are electropositive. Electro is from the word electron and positive shows the positive charge of the cations. For example, sodium. Sodium belongs to group 1A. It has one electron in the valence shell. It needs to complete its octet, so it loses one electron from the valence shell and gain the electronic configuration of nearest noble gas neon. After losing the one electron, it gain a positive charge and it form a cation. So sodium is a metal and it is electropositive because it is losing an electron and forming a cation with a positive charge. Similarly, magnesium also loses the electrons to form the cation. Magnesium belongs to group 2A. It has two electrons in the valence shell. So it loses these two electrons to complete its octet and form a cation with a plus 2 charge, means a dipositive cation. Now you are going to learn about the electropositive character of the metals. The tendency of a metal to lose electrons is called electropositive character or electropositivity. As this property is shown by the metals, that's why it is also called the metallic character. As you can see in the equation, M metal is losing n number of electrons and forming a cation with plus n charge. Means if a metal will lose one electron like sodium, it will form a cation with plus 1 charge. And if it loses two electrons like magnesium, it will form a cation with plus 2 charge. Now the question arises in your mind is that why metals are electropositive? Metals are electropositive because they have large atomic size and low ionization energies. Because of large atomic size, the nucleus holds the valence electrons less tightly and less energy is required to remove the electrons. Means if the atomic size is large, then the ionization energy to remove the valence electron is low and it's become easy for metals to lose the electrons to form cations. For example, atomic radius or size of lithium is 152 ppm. ppm is the unit to measure the atomic size or radii. So it can easily remove the valence electron as compared to fluorine, whose atomic radius or size is much smaller, say 72 ppm. So we can say that lithium is more electropositive than fluorine. Let me recall your topic from chapter 3, that is trends in atomic sizes or radii along group and period. Groups are vertical columns while periods are horizontal rows. Atomic sizes increase along the group because numbers of shells increase down the group. For example, in group 1A, lithium has 2 shells while sodium has 3 shells. So sodium has larger size than lithium. You can also see from the table that atomic sizes are increasing down the group. For example, from lithium to cesium. Lithium is having the atomic size of 152 ppm while cesium is having the atomic size 265 ppm. But atomic sizes decrease along the period because number of shells remain the same but the nuclear charge to hold the valence electrons increase down the group. So the atomic size decrease because of the increase in nuclear charge. You can also see from the table that atomic sizes are decreasing along the period. Like in the second period from lithium to neon. Lithium is having the atomic size 152 ppm while neon is having the atomic size 71 ppm. So the atomic sizes are increasing down the group while decreasing along the period. Let me recall you another topic from chapter 3, that is trends in ionization energies. Ionization energy is the energy required to remove the valence electron. Ionization energy depends on the atomic size. When we move down the group, atomic size increase, and because of this, the valence electrons become far apart from the nucleus, and nucleus can hold the valence electrons less tightly. So because of this, less energy is required to remove the valence electrons. So with the increase in atomic size, ionization energies decrease down the group. But along the period, the atomic size decrease and the nucleus can hold the valence electrons more tightly. So because of this, it is difficult to remove the valence electron. So more energy is required to remove the electron. That's why ionization energies increase along the period when atomic size decrease. Let us learn the topic trends in electropositive character along group. Electropositive character depends on atomic sizes and ionization energies. As we have learned that atomic sizes increase down the group while ionization energies decrease. So it becomes easy to remove the valence electron. Means electropositive character increases. For example, in group 1A, sodium is much larger than lithium. So it becomes easy to remove the valence electron from sodium as compared to the lithium. So sodium is more electropositive than lithium. While in group 2A, if we take the example of beryllium and magnesium, magnesium is more electropositive than beryllium because its size is larger than beryllium. Trends in electropositive character along period. As we have learned that electropositive character increases along the group, but it decreases along the period. Because atomic sizes decrease and ionization energies increase along the period. So because of this, it becomes difficult to remove the valence electron. So we can say that electropositive character is decreasing. As electropositive character is also called the metallic character, so we can say that metallic character decreases along the period. For example, in the second period from lithium to neon, metallic character is decreasing. As lithium and beryllium are metals, means they have more metallic character, while boron is a metallite and carbon, nitrogen, oxygen, fluorine and neon are non-metals. It means that metallic character is decreasing from lithium to neon. Let's learn the trends in electropositive character or electropositivity due to reactivity with oxygen along group. This is also the answer of exercise question number 2 part 1. When we move down the group, reactivity of matter with oxygen increases, means they react more readily with oxygen. For example, alkali metals react more readily with oxygen when we move down the group. Means first alkali metal like lithium form normal oxide because its reaction with oxygen is slow. Normal oxide, the oxide in which the charge on oxygen is -2. You can see the equation in which lithium is reacting with oxygen and is forming the lithium oxide. The formula of lithium oxide is Li2O, while sodium reacts more readily with oxygen as compared to the lithium. So that's why it forms peroxide. Peroxide is the oxide on which the charge on oxygen is -1. For example, you can see in the equation, sodium is reacting with oxygen and is forming Na2O2. Na2O2 is sodium peroxide. In it, the charge on oxygen is -1 and ratio of oxygen with the metal is 1:1 as compared to the lithium which the ratio of the metal with oxygen is 2:1. Potassium, rubidium and cesium reacts more readily with oxygen as compared to the lithium and sodium, and they form superoxide. Superoxide is the oxide with the charge on oxygen is -1/2. You can see in the equation, potassium is reacting with oxygen and is forming KO2. KO2 is potassium superoxide. Similarly, rubidium will form the rubidium superoxide RbO2 and cesium will form the cesium superoxide CsO2. Trends in electropositive character or electropositivity due to reactivity with oxygen along period. As we have learned that reactivity of metals with oxygen increases down the group, but along the period, reactivity of elements with oxygen decreases. For example, in the third period, the first member is sodium. Sodium reacts readily with oxygen at room temperature. Means sodium reacts with oxygen quickly at normal temperature means not much amount of energy is required to react sodium with oxygen. But magnesium reacts with oxygen on ignition means a small amount of energy is required for magnesium to react with oxygen. But in case of aluminum reacts with oxygen on heating means a lot amount of energy is required for aluminum to react with oxygen as compared to the magnesium and sodium. It means that reactivity of elements with oxygen decreases along the period. To learn the next topics, we are going to learn three types of oxides: basic oxide, acidic oxide, and amphoteric oxides. Metals form the basic oxides because these oxides, when dissolved in water, they form the bases. For example, Na2O is a basic oxide. Why? Because when it dissolves in water, it forms a strong base NaOH. Non-metals form the acidic oxides because when these oxides dissolve in water, they produce acids. For example, SO2. SO2, when dissolved in water, it produces a strong acid H2SO4. That's why SO2 is a acidic oxide. But some elements like aluminum form the amphoteric oxides. Amphoteric oxides are the oxides which have both the characteristics of acids and bases. Trends in electropositive character or electropositivity from nature of oxides along group. As I've told you earlier that metals form basic oxides. Along the group, the basic character of metals increases. The metallic character depends on the basic character. If basic character is more, then metallic character is more. Means if the basic character is increasing down the group, it means metallic character is also increasing down the group. For example, in group 2A, basic character or electropositivity or metallic character is increasing down the group. The first member is beryllium. The beryllium oxide is least basic of all the group members. Magnesium oxide is more basic than beryllium oxide. Calcium oxide is more basic than magnesium as well as beryllium. Strontium oxide is more basic than calcium oxide, and barium oxide is most basic of all these oxides. Means when we move down the group, the basic character is increasing down the group as well as the metallic character. Trends in electropositive character or electropositivity from nature of oxides along period. Along period, the basic character of elements decreases. So because of this basic character, electropositive character or metallic character is decreasing. For example, in the third period, the basic character or electropositive character decreases from sodium to chlorine, from left to right along the period. The first member is sodium. Sodium forms sodium oxide Na2O, which is strongly basic, while magnesium forms magnesium oxide, which is basic. Aluminum forms aluminum oxide, which is amphoteric. Amphoteric oxides are those which have both the properties of acids and bases. Silicon forms silicon dioxide, which is weakly acidic. Phosphorus forms phosphorus pentoxide, which is acidic. Sulfur forms sulfur dioxide, which is strongly acidic, while chlorine forms chlorine heptoxide, which is very strongly acidic. As you can see from the table, the basic character is decreasing while acidic character is increasing along the period. I hope so you have learned the trends in metallic character or electropositive character. Now you can easily do the example 8.1. In this example, you have to identify the more metallic element. In the A part, from sodium and potassium, potassium is more metallic because metallic character increase down the group. And as potassium comes after sodium in group 1A, therefore potassium is more metallic. While from beryllium and sodium, sodium is more metallic. The reason is that metallic character is more if the atomic size is larger. As beryllium has 2 shells and sodium has 3 shells, therefore the sodium has larger size as compared to beryllium and sodium is more metallic. Let's do some question from self-assessment exercise 8.1. In the first question, we have to identify the element which is more metallic. In the A part from beryllium and boron, beryllium is more metallic. In the B part from silicon and aluminum, silicon is more metallic. In the C part from potassium and lithium, potassium is more metallic element. Let's do some more questions from self-assessment exercise 8.1. In the first question, we have to rank each set of elements in order of decreasing metallic character. In the A part, from sodium, lithium, and potassium, lithium is least metallic, while potassium is the most metallic element. In the B part, from aluminum, sodium, and magnesium, sodium is most metallic and aluminum is the least metallic element, as you can see here. In the next question, we have to tell which is more basic, lithium oxide Li2O or sodium oxide Na2O. Na2O means sodium oxide is more basic than lithium oxide. The reason is that sodium oxide, when dissolved in water, it forms a strong base, sodium hydroxide, as compared to the lithium, which forms lithium hydroxide. Sodium hydroxide is a much stronger base than lithium hydroxide. That's why sodium oxide is more basic oxide than lithium oxide. Let's do some question from the exercise. Question number 2, part 2. Which element is more metallic, magnesium or aluminum? Magnesium is more metallic than aluminum. Magnesium and aluminum are both from third period. Metallic character decrease along the period and magnesium comes before aluminum in the third period. Therefore, magnesium is more metallic. Question number 3, we have to arrange the oxides in order of decreasing basic character. Strontium oxide is the most basic oxide while beryllium oxide is the least basic oxide. Question number 4, we have to rank the each set of elements in order of increasing metallic character. In the A part, lithium is least basic or least metallic while potassium is most metallic. In the B part, aluminum is the least metallic and sodium is the most metallic. In the further topics, we are going to learn the comparison of the reactivity of alkali and alkaline earth metals. For that, first we should learn about the position of alkali and alkaline earth metals in the periodic table. You can see two boxes on the extreme left side of the periodic table, one green box and the other one is red box. In the green box, the group 1A elements except hydrogen are alkali metals, while in the next box, in the red box, group 2A elements beryllium, magnesium, calcium, strontium, barium and radium are alkaline earth metals. To learn the next topics, we are going to learn three types of oxides: basic oxide, acidic oxide, and amphoteric oxides. Let's learn the electronic configuration of alkali and alkaline earth metals. Alkali metals, say lithium, sodium, potassium, barium, and cesium, all have one electron in the valence shell. As you can see in the diagram, lithium, sodium, potassium, barium, cesium all are having one electron in the valence shell, although the valence shell number is different. So their general electronic configuration is NS1. But alkaline earth metals, say beryllium, magnesium, calcium, strontium, barium, and radium, all have two electrons in the valence shell. As you can see in the diagram, there are only two electrons in the valence shell. So their general electronic configuration is Ns2. To learn about the reactivity of alkali and alkaline earth metals, we should learn about the ionization energies of alkali and alkaline earth metals. As you can see in the table that alkali metals, say lithium, sodium, potassium, barium and cesium, have low ionization energies as compared to the alkaline earth metals, which are beryllium, magnesium, calcium, strontium and barium. For example, lithium. Lithium and beryllium. Lithium is having 520 kilojoule per mole of ionization energy, which is much smaller than beryllium, which shows the ionization energies of 899 kilojoule per mole. Same is the case for all other members. Ionization energies of alkali metals and their reactivity. Reactivity of alkali metals depends on their ionization energies. Ionization energies of alkali metals are very low. That's why they have great tendency or capacity to lose the valence electron. They have one electron in the valence shell, as I've told you in the electronic configuration that all alkali metals have one electron in the valence shell, so they can easily lose that electron and form a cation with +1 charge. They are so much reactive that they are never found in the free state in nature. So, alkali metals are always kept under the kerosene oil to prevent them from reaction with the moisture in the air. They show increase in the reactivity down the group because ionization energies decrease down the group, so they can easily lose the valence electron and shows the increased reactivity. For example, ionization energy of sodium is lower than lithium. So, sodium is more reactive than lithium as it can easily lose the single valence electron. Ionization energies of alkaline earth metals and their reactivity. The reactivity of alkaline earth metals depend on their ionization energies. Ionization energies of alkaline earth metals are also low. That's why they have great capacity or ability to lose the valence electrons. As I've told you in the topic electronic configuration that alkaline earth metals have two electrons in the valence shell. So they lose those two valence electrons and form a cation with +2 charge. The cation with +2 charge is called a di-positive cation. Di is for the word 2. They are less reactive than alkali metals because their ionization energies are higher than the alkali metals and it is difficult for them to lose the valence electrons as compared to the alkali metals. They are also kept under the kerosene oil because they are so much reactive they can react with the moisture of the air. Alkaline earth metals also show increased reactivity down the group. As the ionization energies decrease down the group, so the reactivity of alkaline earth metals increase down the group because it is easy for them to lose the valence electrons. As the ionization energy of magnesium is lower than beryllium, so magnesium can easily lose the two valence electron and it is more reactive than beryllium. So we can say that reactivity of alkaline earth metals increase down the group when ionization energies decrease. For further topics, we will continue with the part